Good evening, everyone. Welcome to episode 6, the non-homogeneous equation. I'm sure your first thought is that this is not episode 6. It says episode 4 appendix, another approach. That's exactly what it is. I'm going to begin with this because episode 6 is relatively short, and I feel like this is crucial to understanding episode 6. So basically, when I left off on episode 4, I believe that the explanation that I gave for why our general solution only has two independent solutions as part of it was lackluster. It was unconvincing. It was unconvincing to me, and so I made this episode 4 appendix over a week ago actually, but I never recorded the video for it because I still actually didn't even get it after making these slides until yesterday whenever we actually used our particular solution. We actually evaluated a second order equation and found a particular solution for it. And so, yeah, watch that, and this will make a lot more sense to you. Episode 5. So let's get started on this. So we got to remember that we get two initial solutions for a second order differential equation whenever we're trying to find its particular solution. All right. The entire reason for the rest of this is because of those two solutions. I'm going to show you guys some algebra that isn't particularly crucial to know, like to memorize or anything like that. But the point of me showing you all of it is that it's going to show you that the two arbitrary constants that we end up with are designed in order for us to find these two particular solutions, or not particular solutions, these two initial values right here. We need to account for those initial values whenever we take a particular solution. So, yeah. So, just this right here, this is one of the things that you need to know. Then this right here, we're going to call the initial values of this. So basically, our y initial at A is going to be this, and the rate of change of y initial is going to be this. And then so what I'm going to do is that I'm going to multiply both equations by something here. For this one right here, for our A equation, it's going to be this. For our B equation, it's going to be this. And then we're going to subtract them like a system of equations, and then we're left with this. Then we can divide both sides by this bracketed part right here, and then here is our constant, our first constant. Just pay attention to the fact that this on the denominator right here is our Wronskian formula. So if our Wronskian equals 0, then this is undefined, and we lose one of our arbitrary constants. So that's part of the reason why, that is the reason why our Wronskian can't equal 0 for, something, two functions to be considered worthy for the general solution, right? So I'm going to do a similar thing here, except with our A equation and all that, and our B equation, I multiply it by this and this. Just know that whenever we are multiplying this, it makes this, and then this and this the same term, so then it cancels out and it leaves us with just this. So then we have this, very similar to the last time. Then we divide both sides by this bracketed part, and then now we have this. This isn't exactly the Wronskian equation, but it's the magnitude of the Wronskian, so that's all you need to know whether or not it's 0, because then if it's anything other than 0, remember, then the two functions that you're comparing are linearly independent of each other, and thus are worthy for your general solution, right? So, yeah. Here, we know what our C1 is, and we know what our C2 is, right? And so we know that the C1 and C2 are going to help guide us towards our initial conditions. All that we need for our particular solution is to be able to tweak these two constants right here in order to get to it. So the thing is that with our existence uniqueness theorem, we know that for every single initial condition, set of initial conditions that we put forth, there is going to be a solution for it, and that solution is unique. The thing is that with this equation right here, and with the equation that I showed you earlier, I didn't give a specific set of initial conditions, right? I just gave like variables, right? So any initial condition can be plugged into that. Ooh, oh my gosh, that's embarrassing. And this will work. So basically, that's exactly what a general solution is. This is every particular solution, but you just need to adjust these for that. So yeah, that's why this right here is a general solution. So then why not just one equation? Why not just one equation for the general solution for a second order differential equation? It's because then you can't account for the other initial condition we have, which is the rate of change at t equals 0 for y, right? So That's why we need the second one. If you were to introduce a third one into this, then it's just going to be redundant, because the point of this, as I showed earlier, is that this is going to be able to cover every single particular solution for any set of initial conditions that you put forward. Alright, guys, I'm going to break the fourth wall. This is a thank you for watching moment, but the video is not done. We have episode 6. So yeah, sorry about that. If that was scary for you guys, that gave you like an existential crisis, made you disassociate, sorry about that. But so yeah, here is the non-homogeneous equation. Right here. Here he is. So it's the same thing with the homogeneous second order equation, except we have a g of t on the right. And just to let you guys know that this is still linear. We're going to be really utilizing our linear properties to our advantage again for this. So how do we solve this? I'm going to give you guys a hint. So here's an equation right here. Here is a non-homogeneous first order differential equation, and this is a solution right here. I didn't show any work for this because if you guys want to see the work that's covered in episode 2, we actually do an example very similar to this in episode 2, except the t is not the t is not negative there, I believe. Or maybe I mixed it up actually, but it doesn't really matter. Just, yeah, it doesn't matter. So this is our solution to that. And then here is the homogeneous equation. And so notice that it is very similar to our previous one, except it's missing the plus 1/2. So this right here is the general solution to this right here, but then we add, you know, something a bit more, you know, for this. You know what I mean? So we're going to approach our non-homogeneous second order equation a similar way. So here is the homogeneous second order equation. Here's the general solution for that. And so here's our non-homogeneous, and this is what I posit as a general solution for that. But Sensei Colonel Matt, didn't you just get done telling us that, you know, it's only going to have two independent solutions for the general solution? I know, I did say that, but the thing is that this right here is only a particular solution, alright? This is not something that's going to compromise our linearity or anything like that. This is like, so please recall the explanation that I gave for the two-dimensional solution space in episode 4. I talked about how basically we're creating like a 2D plane, and each axis is our y1 of t, and the other axis is our y2 of t. What this is going to do is not add another axis to it, which would not be, we shouldn't do that. That's just going to ruin everything. What this is going to do is basically just off-put the plane. This is going to off-put our axes. This is like a graph modifier right here. So it just kind of moves our square for, you know, our little plane wherever it needs, or it adjusts it, so that we can account for this right here. So this is just a solution for the non-homogeneous equation, a particular solution for it. All right. So let's move on. That's why you notice there's no C3 here, because this is not going to help us with, you know, satisfying any of the initial conditions in the same way that these guys do. So I'm going to show you guys some proof for why this works, because I'm sure you guys might be a little confused right now. So imagine that we have two solutions for our non-homogeneous equation. All right. So using our linearity, we know that this and this are the same thing. So L of k of t, this is the operator for the non-homogeneous equation. It's going to equal g of t instead of 0, right? And so then we subtract it by this. So then we get g of t minus g of t, which is equal to 0. And so that's a nifty little reintroduction of our linear properties from episode 4 or 3, I think. I don't even remember. That help us out. And so you might be wondering, wait, isn't the linearity property, shouldn't this just be... Remember, this is not the homogeneous equation. Because in the last episode, I was telling you guys that for the solution of something with complex roots, you don't have to worry about the second root about it, because whether or not it's plus imaginary sign beta t or minus imaginary sign beta of t, it doesn't matter, right? Because we are solving for a homogeneous equation there. the reason it wouldn't matter because it's the difference between 0 plus 0 or 0 minus 0. So that's why that works. So it is very different from this. So don't get confused. This is, so our k of t minus e of t, which I'm just now realizing that this is kappa of t and epsilon of t, oopsie, is not equal to hooray. It is actually equal to this right here is actually a solution for our homogeneous equation, because look, it equals 0, right? So this right here is a solution to the homogeneous second order differential equation, all right? So why does this matter? Look at this. So let's just create something new that we can just call, like, I think this letter is psi of t. Psi of t is equal to y of t minus phi of t. And then these two things are solutions to the non-homogeneous equation, all right? So the thing is that we can reorganize this stuff right here and then recognize that this right here, this is the solution to our homogeneous equation, right? Like I just described in the last slide. Imagine this is the kappa of t and this is the epsilon of t, right? So we can just reorganize everything here. This is a solution to our non-homogeneous equation equal to the solution to the homogeneous equation plus another solution. So the thing is, we can remember that this is this because it's a solution to the homogeneous equation, and then we can plug everything back in, and then look, this is our solution to the non-homogeneous equation. That's pretty crazy, right? And then so now what we do, how we tackle our war from here is that, so here is an example. So here's one of our things right here, non-homogeneous second order equation. We need to first find the solutions to the homogeneous side of it, and then just find a particular solution that satisfies the entire non-homogeneous part. That's all we need to do. So first let's find the solutions to the, as if this was homogeneous, as if this was a 0. Imagine that. And then so think about this. We already did this as an example, like a couple episodes ago, and we, if you guys recall correctly, our two linearly independent solutions are cosine of t and sine of t. And so now we just need to find one particular solution of this. What can we get the double derivative of plus itself that equals t? It's t. The double derivative of t is 0 plus t is equal to t, right? So nothing too crazy there. And then so now our general solution is this, which is not crazy at all. So going back to the whole, does this compromise our integrity? Does this compromise the two-dimensional solution space? Not at all. Just think of this right here as less of a linear, this is not a linearly independent solution right here, where no one's saying it is. It's just something that we use to adjust the 2D space right here so that this whole thing can solve for the non-homogeneous version of the homogeneous equation, right? So nothing too crazy there. This is the example. So thank you guys for watching. I hope you guys enjoyed the episode. Let me know if you have any more questions. Thank you.